Today we have with us Fabian Scheurer. I think there is a group of people that knows him very well because he's another tutor on the Open Thesis Fabrication program. We're glad to have him as a faculty and as a tutor this year. Fabian Scheurer is one of those crazy people that they are not architects. They are computer scientists, but they do architecture, and these kind of people we really like. And he has been collaborating with several architectural offices trying to make reality the sketches of us, our sketches, the sketches of architects. So just to read a bit more about him, Fabian Scheurer, he's from Munich, is founding partner of Design-to-Production and leads the company's office in Zurich. After graduating from the Technical University of Munich with a diploma in computer science and architecture, he worked as assistant for the university's CAD group, as software developer for CAD-provider Nemetschek, and as new media consultant for Eclat in Zurich. From 2002 until 2006, he studied the use of artificial life methods in architectural construction as a member of Ludger Hovestadt CAD group at the ETH Zurich, and managed to transfer the results to a number of collaborative projects between architects, engineers, and fabrication experts. In 2005, he co-founded Design-to-Production as a research group at ETH to explore the connections between digital design and fabrication, which is a new model of let's say, practice that has arisen after all the CAD and CAM techniques. So thank you very much for being here with us, Fabian.
Oh, okay. Hello. Thank you very much for the introduction. I'd rather stand up while talking. I hope that doesn't disturb anybody. I've been told to talk about 45 minutes. Unfortunately, I've been told to talk 45 minutes about 10 seconds ago, so I've got lots of slides for you. And I'm going to shoot them at you at high pace, so I hope I won't bore you, and I hope you can follow. I've been introduced already, so I can directly start with project. And I start early on. As has been said, I was working at the ETH Zurich, at the CAD chair there, for a couple of years, and this basically is the first design-to-production project ever. Actually a university project that we built for the Swiss Bau Fair in Basel in 2005, out of the university's computer-aided architectural design chair. And the goal actually was to prove that there is something like a digital chain from design to production. So this is a small sphere about 4 meters in diameter. The idea was to have the sphere and a few square openings in that. And as has been said also, I was working on methods for artificial life or self-organization for construction principles. And this is basically the principle behind this sphere. There's a quadrilateral mesh growing on this sphere. In this little video you can see it here in real time, more or less, based on a few simple rules that ensure that the thing is always quadrilateral. And that was not just a nice idea. Triangulating a mesh is easy. Making a quad mesh on a sphere is difficult. No, the question also was, how do we build this thing in the end? The outcome of the software looks like this. This is basically the optimization result, and you can see that the edges of this mesh nicely align with these openings that we wanted to have in the end. A colleague of mine did a bit of scripting and translated this into a fully detailed CAD model of the whole thing. Then we put it down flat, all the nice pieces that had to be fabricated, generated fabrication code for a CNC cutting machine directly from that. Cut about 1,200 pieces, put them together in quadrilateral frames and stacked them like a big puzzle, one on top of each other. Looks pretty simple, actually looked pretty nice until we had to put this black membrane on top because one of the sponsors was a fabricator of membranes. The other sponsor was fabricating windows, as you can see. This is what it looks from the inside, much more interesting. So it's all quadrilateral frames, and the trick was that we had to fulfill certain requirements concerning the size or the length of the edges and the angles in which the four boards meet at the corners and stuff like that, and that was all embedded in this growth algorithm, basically, which was great for me because I was able to prove that my optimization software was working. But also I learned another lesson, which is this so-called digital chain from optimization to digital detailing to digital fabrication, which is shown to you in slides of software representatives in this way, actually looks like that. It doesn't work that easy. There's a lot of handwork, manual work involved. There's actually a lot of project-specific programming involved because those interfaces simply don't work by translating one into the other and just shifting IGES or DVG or DXF or whatever files from A to B. Doesn't work. One hint why that is the case is pretty obvious. There's too many degrees of freedom in the fabrication. If you have a laser cutter, you have two axes, X and Y. Degrees of freedom of the laser cutter, and you have two dimensions in the material. Matches perfectly. Nothing can go wrong. If you have a three-axis mill, you have X, Y, and Z degrees of freedom in the three-axis mill, and you have three dimensions in the space you're working in. If you have a five-axis mill, you have still 3 degrees of freedom in space, but 5 degrees of freedom in the machine. So, oops, things become ambiguous. Someone has to decide whether it's better to drive to this point from the left or from the right or from the top or from the bottom, which means software is not a good friend of yours anymore because this is getting too complicated. You need to know a lot about fabrication before you can start to work with a 5-axis machine, let alone a 7-axis robot like the one out there. So this automatic translation from, oh, we have a geometry here and we need a fabrication code for the machine on the other side, and we just push a button is not working. Very small, very early project, very, very good lesson learned there, almost 7 years ago. Next project, still at the ETH, was this. This is an exhibition platform for the 4 schools of architecture in Switzerland. It was a traveling exhibition going once around the world, designed by a small practice in Zurich, Instant Architekten. Client was the ETH in Zurich. Fabricator was Bachheiden, the carpentry that also built the sphere you've seen in the last project. The thing is 40 meters long, 3 meters wide, and it's basically a landscape model. It's an abstracted cross-section through Switzerland, following the path along Geneva, Lausanne, Mendrisio, and Zurich, where the 4 architecture schools are. It started like this in the designer's office as a 1:50 model from cardboard and foam. And the question was, how do you build this on a real scale? I mean, there's a default approach for building landscape models, which is 3-axis milling. So you have whatever material, and you have a 3-axis machine, and you mill away a rough cut and a fine cut, and in the end it looks like that, the Matterhorn. Pretty straightforward. Question only is, if you have a 1:50 model, and it takes about 1 hour of milling time to do that on the machine, how long does it take to mill the 1-to-1 thing on the same machine? Any guesses? It's actually pretty simple math. It's 50 times wider and 50 times longer and 50 times higher than the model. Times 1 hour is 125,000 hours, is just a bit over 13 years. Which means, no, not on the same machine. You cannot mill this out of foam and then coat it with fiberglass or whatever to walk on. You have to think about fabrication methods that are different than the model. Which means, oops, you can either try to find a 50 times bigger machine, This is pretty much the largest 5-axis mill I've seen in my life. It's in Norway in a boat builder's workshop. They're milling foam cores for race boats on this. Usually, at the time we were visiting them, they were milling the balconies for the Oslo Opera by Snøhetta out of oak. If you have a 50 times bigger machine, you have to have 50 times bigger tools if you want to reach the same speed, which means your little tiny milling bit is becoming a 50 times wider. This thing is only 15 centimeters in diameter, milling tool, which gives you a much lower resolution than you had with a smaller tool. You're seeing the traces here. And to reach the same speed again, in terms of I want to mill the whole thing in 1 hour, you have to move this tool at 50 times the speed than the small machine, which means you have to accelerate it on this end of the machine, like a Porsche on a German Autobahn, and then you have to make full stop on the other side, 15 meters to the back, turn around, and go back, which is physically impossible. So instead of finding a 50 times bigger machine, we took a different approach. We took the cookie cutter, as we call it, and cut the whole thing in vertical slices of 40 millimeters. So 40 meters divided by 40 millimeters is 1,000 slices. You get 1,000 individually curved rafters if you lay them out flat, 90 degrees on the side, and nest them nicely on 126 boards of 40 millimeter MDF. You can cut them on a 5-axis machine, one by one, and stack them nicely, like this. And you see there's a little detail here that sits on a vertical piece in the end, and you have little dowel holes that ensure the positioning of one piece next to each other, and then you can just put them one next to each other. They're nicely numbered, of course, and you get your platform. And then you put an Alphorn blower on top of that, representing Switzerland somewhere in San Francisco at the opening of the first exhibition, and there you are. The nice thing that happened here is that by having those beams coming from the left and to the right and basically overlap in the middle where the people were supposed to walk on, we didn't even have to paint the path and keep people from walking on the sides because no one will step on that. There's gaps in between. It works like, the cows won't go over these grids. Swiss tricks. So next lesson learned, you cannot scale things. Volume is proportional to scale to the power of 3, which means weight, cost, time, everything goes up like this. If you can produce something on a model scale, it doesn't mean nothing for a 1-to-1 scale. You have to think again if you want to blow it up. So, next project, still university. 1 year later, the University of St. Gall approached us to build a sculpture for Daniel Liebeskind, who had designed this thing as sort of a representation of the future of the city, because he was hosting a workshop at HSG in St. Gall, Futuropolis. They had tried to find somebody to build this within reasonable budget and time and didn't manage to, and one of the doctoral students at the HSG who was at the ETH beforehand called us up and said, hey, you're doing crazy stuff like this. Any ideas? The design looked like that in this stage. So you have this sort of sculptural volume here with, I don't know, intersecting planes, halfway transparent. This gives you a hint what actually was expected to build almost 100 of those towers that you could put together to form this volume, but you can take them apart also. In the first round, I thought of building this out of steel plates, which was completely immobile, because it would have probably had a couple of 100 tons. The next step was to find somebody who could make it out of timber. And the idea behind it, and in the end, of course, it was timber. The idea behind it is you have 98 of those towers, and you have about 600 boards of birch wood who cut these towers at an angle And the dark red part here is inside the tower, and the lighter red parts are already in the neighboring towers, which means you have a continuous grain of the wood through the whole structure, which leaves you at 2,000 and something timber pieces to be cut up, which is not a problem. You can build a parametric model of that. You can automate the planning process more or less. You can find a 5-axis machine with a saw blade to cut up the things, and you nicely chop up 12 cubic meters of birchwood until you end like that. And then a second problem arises is how do you put it together again? Because in the end you only want to have 100 parts and not 2,000 something. Fortunately, the specialist carpenters we were working with came up with this little detail here, which is an aluminium dovetail connector. They're standard parts. They come off the shelf either in small pieces or in meter-long things that you can cut up yourself. And the good thing is you can cut those notches that you need to connect the pieces directly on the 5-axis machine we used for cutting up the pieces also. And that saves an enormous amount of time just by the fact that usually if you want to connect timber pieces, you have to put glue on both ends, and then you put them together, and then you have to clamp them and wait until the glue dries for at least half an hour until you can work on. One of the towers contains about 20 timber pieces. If you wait half an hour after connecting every single piece, it'll take a year or two to build the whole thing. Now you can put glue on both sides, put them together, drive in the dovetails, and then you're done. And then you can go on to the next piece. And this is how the notches get milled on the machine. This is how the assembly actually looks like, with nice little Lego-like plans, numbered pieces again. And the problem, of course, is you have to come up with some sort of systematic detailing. You have about 3,500 joints in there. And at first sight, they all look different. If you look closer, you identify only 10 different types of joints, and you only have one detail, namely this little dovetail joint here. Only because they're cut at more or less arbitrary angles, they look this distorted. And also almost look like a design feature in the end, which is much better than having screws all over the place. This is the end result. And the question here is, of course, okay, you have to come up with those details that save you a lot of time. If they only save you 2 minutes of waiting at 3,500 connections, you've saved a couple of days' work in the end. So you actually have to, up here, at least up here, when you come up with the parametric modeling of the detailing, you have to know about all the assembly process in the end, or you have to start thinking about that. Basically, you have to know about the fabrication and the assembly to come up with the detail, to develop the detail to go into parametric modeling. Even better, you know about this at the design stage already, which is difficult. This is basically what we're doing. We're trying to swim upstream, know about fabrication, know about the detailing, know about the assembly, know about the whole process, and try to help finding nice little intelligent, simple details in the first place. Okay. Scaled it up a bit. This is the EPFL Rolex Learning Center, aptly named after the sponsor. Money was not an issue there. By Sana, engineers Bolling and Grohmann, general contractor Losinger, and we were actually only involved in the formwork for this concrete slab you see there. The whole thing is a one-story building, basically, with 20,000 square meter footprint. It's a library, working space, cafeteria, basically a learning center. And it's a steel structure with a 9 by 9 meter grid of columns that stands on a large concrete slab that is undulating up and down 6.5 meters. This is a rendering from the competition. And the good thing with concrete, of course, is you can cast it in any shape you like. The bad thing is you need something to cast it into. which means you need 7,500 square meters of formwork to cast in a couple of thousand cubic meters of concrete. The idea of the engineers and the general contractor was to divide the 7,500 square meters into 2.5 by 2.5 meter squares. And on every of those 1,500 squares, there is a timber box built from 6 or 7, depending on the inclination, vertical timber cleats, and on top of that, a sheet of plywood. And the whole thing is standing on a standard scaffolding tower that's missing in this picture here. So you scaled it up, and you have 1,500 boxes, and that means you have about 10,000 of those timber cleats, and unfortunately, they're all individual. Which means you need a digital model that holds all of those 10,000 pieces, because everything that has to be digitally fabricated in the end has to be digitally modeled first, which is a pretty big size for a model. So this is 10,000 timber pieces in there with a bit of detailing, something that you actually have to hold in a computer's memory, which is not that easy. But out of this model, you can then, of course, extract everything you need. You can extract 1,500 drawings for the single boxes, for the assembly and the quality management. You can extract whatever lists you need for ordering the scaffolding towers or the material or setting up the formwork or whatever. You can extract actually the machine codes again for cutting all those 10,000 pieces, which look like that. This is one of the pieces with the numbering nicely. You can nest that all on raw material and then put it into a 4-axis cutting machine, number it nicely, and hopefully don't make mistakes. We always urge people to actually mill the numbers into the pieces. Usually they won't do that because it takes too much time. They have to change the tool, and then they have to mill the number. It again takes a few seconds. At 10,000 pieces, a few seconds per piece make a difference. But then you have to be pretty sure that the guy standing right next to the machine is writing the right numbers onto the pieces in the right place. But because sometimes it's really hard to see, they're almost rectangular, what the orientation of the piece in the final assembly is going to be. Yeah, you stack them nicely, and then you transport them a couple of 100 kilometers from the cutting to the formwork contractor. And then they start assembling boxes, one after the other, with a little jig here so they don't have to measure, which is very intelligent, because at 1,500 boxes, if you have to measure all the pieces, it's stress. Now here, you just have this steel jig around, you put in those yellow timber beams, and then you shoot the thing together with your nail gun. There you go. They're 2.5 by 2.5 meters, simply because that fits on a standard truck nicely. Every single one of them gets a little sheet with, of course, the table number and basic measurements in the corner for quality control in the factory and on site. So there's the absolute coordinates above sea level here. You can basically put a geometer on every corner of the formwork and measure if it's all right. You can sign it off if everything's okay. Then you stack them on trucks, 150 truckloads from close by Bern to Lausanne. And then you put them on the scaffolding, one after the other, have a smoke. It looked pretty impressive, I have to say. It's got two parts. It's the smaller part up here, basically finished. This is the larger part, where you can see here is still the scaffolding. Here the table's already there, and here the rebars are already in. The interesting thing is that for quality reasons, the whole thing was cast in one go. So the whole area here was actually one casting. It took about 48 hours, I was told. I wasn't there. And they had a constant flow of concrete trucks just coming in, pumping all the time. Then you take out the formwork, which is not needed anymore. It's actually our first big timber building that we did, but unfortunately it's not there anymore. Here, this is it. And this is what it looks like now. So probably the next lesson learned from this project would be only lean models are good models. I'm not talking about Naomi Campbell, I'm talking about digital models. You have to put everything that you need to cut, drill, whatever on a digital machine into a digital model. Doesn't help. Anything that is not defined on a digital side in the model is not being cut on the machine. So you need a model that holds 10,000 timber cleats in this case, which means you have to really think about what you put into the model and what you leave out of the model, because it makes it clumsy and slow and too fat to stand upright if you put in just everything you know. You have to really think about what you leave out. That's the main problem in many of the projects we were working after that, because they tend to get bigger and bigger and bigger, you'll see. But in the first place, a little step back to a very small project, one that we did together with the Technical University in Trondheim in Norway. It was a very important project in two respects. First, it was our first real timber project that we tried to work on those kinds of machines, digital joinery machines for timber building. Usually what they do is they do roof trusses and stuff like that. So this is two different machines of the same brand. The brand is Hundegger. They're holding about 90% of the world market share, so you'll hardly see any other machines like that in the timber industry. Nevertheless, I'm going to show you a different one later on. The machine is basically this here, and then you have 10 meters to the left and 10 meters to the right, or even more, where you feed in beams, and then you have those things here, little milling tools of about this size, or circular saws or other milling tools, stuff like that, cutting details into timber beams that you then can put together roofs or log houses or stuff like that. Fully digital, total standard in the timber industry. So there's lots of those machines out there doing standard timber detailing. And we wanted to test that. We have never worked on a machine like that before. We only knew carpentry machines doing cabinets and smaller stuff. So we took 15 students and did a design competition in Norway, and they came up with, after the competition, the design for this twisted box for a camera obscura that is in Trondheim Harbor still. The interesting thing is it's twisted, but it's made of only straight pieces, which I find very, very compelling. And this is just a nice little project on the side. I just wanted to show this. This is the whole gang with the proud end result. They managed to do that within 3 months. In the fall of 2006, basically this picture was taken, I think, 8th of December 2006 at 12 o'clock noon. The sun rose just half an hour before and was gone half an hour later. This is pretty far up north here. But it led directly to this project. We were so happy with working with timber, but we were pretty unhappy with working only with straight sticks. So we decided to call up all the timber fabricators that we could find that ever worked on curvy stuff. And the second, I think, that we called up was Holzbau Ammann, who worked on the big roofs for the Expo in Hanover 2000. You probably have seen them by Thomas Herzog. So we found this project, we found the name of the timber guys, we called them up and said, hey, we would like to do a presentation at you because we want to show you what we're doing and we want to do a project together. And then we walked in, managed to do half of the presentation, and I stopped and said, you can stop now. We just signed the contract for this, and we have no clue how we do it. The Centre Pompidou in Metz by Shigeru Ban. As I said, Holzbau Ammann did the timber roof. SJB is the engineer, and Kreasio Holz is the consultant. And it was really interesting because there's a long, long history behind this project. I'm not going to tell it here, but it was almost dead a year before we entered this project. And then a couple of Swiss timber engineers in the end found out how to build it in principle. But they've never done something like that before on their machines, so it was really difficult to actually get the digital side of the whole thing running. The project is based on this Chinese straw hat. The legend says Shigeru Ban found it on the flea market in Paris and liked it very much. If you look closely, you see this triagonal, hexagonal pattern that you can find here. It's proudly displayed in Metz, where I took this picture. So this seems to be the original straw hat inspiration. Oops. The only thing is, when Holzbau Ammann entered this project, they got the geometry as a 3D model from the engineers, and what they gave him was a DXF file with straight lines connecting those points here. What Shigeru Ban wanted, and you can see that, is continuously curved beams, which is sort of a discrepancy here. We tried to smoothen out the worst kinks by a bit of dynamic relaxation. So we took the whole thing as a minimal surface or a membrane basically and tried to relax it a bit, which worked actually quite well, but came too low in a few corners over here where the surface obviously had been designed to fit the HVAC underneath. All the climate things didn't fit after we relaxed the thing. In the end, we actually needed help from specialists from the automotive industry to take this relaxed point cloud and reconstruct a nicely continuously curved NURB surface that we could use as a reference for the geometry of this straw hat. To then, from that, generate about 18 kilometers of continuously curved girders, which is pretty straightforward if you know the rules to follow, but leaves you at the next problem. Those things are up to 80 meters long. To fit through a fabrication machine and on a truck to be transported and to handle them on site, you have to chop them up into smaller pieces. This is the machine that was basically creating those things. You can see a rather straight beam here. This is the raw side. This is the already machined side. Here in the back somewhere is this aggregate just doing connection details here, and this is the planing tool used to cut down the pieces. The cross section is about 14 by 44 centimeters. So there's nothing like weaving anymore in a straw hat. Those are really stiff. That means they have to be cut into shape before you bring them to site. And there are a few constraints concerning this segmentation process that we had to go into. One of them is an economic side. You can cut a curved thing out of a straight beam unless it's too curved. If it's only slightly twisted, no problem. You cut away probably 20 to 25% of the material, and then you have your curved thing. A straight glue laminated blank comes at around 400 euros per cubic meter. If the thing gets more curved, it doesn't make any sense to actually cut the whole curved thing out of a straight beam because you're cutting away 80% of the material. And what's even more important, you're cutting the fibers of the material. If you cut a curved thing out of a straight thing, you're cutting the timber fibers, which means you're actually cutting away the strength of the piece, which you need to get the roof standing. So you have to laminate a curved blank to mill the curved piece out, which comes at more or less double the price. If it's even more curved, you have to laminate a double curved blank, which is possible, but comes at 6 times the price. So it makes a real difference to decide where to cut those 80-meter long beams into segments, because that means due to the geometry of the part, it can be fabricated from either a straight or a single curved or a double curved beam at 100%, 400%, 200% or 600% the price. which is a nice optimization problem. Next to a few others, those pieces have to be short enough to fit on a truck, they have to be straight enough to fit through a machine, and a few other things. There is a long back and forth between the engineers, the fabricators, ourselves, and anyone else involved in the process. But in the end, you have pieces like that go into CNC fabrication. This is only a small sample. It's been about 1,800 of them. This is what a doubly curved glue lamp blank looks like. If you look very closely, you see that this is actually laminated together from 2 by 2 centimeter lamellas, if you want to call them. This is what the planing process looks like. There you have this disc with about 40 centimeter diameter, taking away the material. And this is one of the finished segments with a nice number. This time they milled it into the piece, fortunately. Also, there's a little sheet of paper here that says, gives you a bit more information about the pieces. This is the connection at the crossing point. There's a hardwood pin glued into this hexagonal hole. And those hardwood pins are then placed on top of each other with a threaded rod in the middle and pre-stressed together. And at the butt joints, there's the slot plates here. And all the detailing is directly fabricated on the machine again. So every single hole for the slot plates is already fabricated on the machine, which gives you an idea about the precision that you have to reach here. The codes and standards say that you have to be within about 0.3 millimeters for drilling those dowel holes there. And this is the precision that the machine actually can reach. But this is also the precision that the model has to have that feeds the machine. You put up scaffolding, laser measured in place, and then layer after layer you put the things on top of each other and bolt them together. You can see the ones in the roof are made of spruce, the ones going down to the ground are made of larch, simply because they're more exposed to the weather, and larch is more resistant to that. And you see all the dowel holes where the slot plates are connected. And this is what it looks like in the end. Was opened in 2010, I think. The interesting thing is the exhibition is in those 3 concrete boxes actually sticking through the roof. The roof itself is just a weather shell, let's put it like that. There's only those polycarbonate garage walls going up there. This is actually an outside space, so it's not heated. There's a PTFE membrane on top. The whole thing is a very, very expensive straw hat. Our lesson learned is the input quality has to match the output quality. If you have a machine in the end that's able to do things precise down to a few tenths of a millimeter, the input has to be even more precise because you're losing a bit in the middle. So you have to actually have a digital model of your 7,500 square meter roof that is precise within a few hundredths of a millimeter, because every error in the model is going to be duly reproduced in the final piece. Every kink you have here, you're going to see over here. Which means if you think that you can just send off your architecture rendering models to the fabricator and then swipe your credit card through the slot and order a roof like that, it's not going to work probably. Almost in any project we're working on, we have to regenerate the geometry of the things from scratch, which is not meant to be architects bashing here. It's simply no architect is paid to build models on this level of precision, and so they don't. The engineers are not paid for that, and they don't need to do that, so no one does it. Only at the fabricators at the very end, someone needs to have a model like this. And unfortunately, no one wants to pay for it, but that's a different thing. But directly after that, we ran into the next Shigeru Ban project, a very expensive golf club in South Korea, in Jeju, with the same team, only the timber fabricator was different because the other timber fabricator was still running 24/7 his machine on the Centre Pompidou in Metz, so he was busy. We needed another one. This time it's more regular. This is a very rectangular grid of 9 by 9 meters with 32 elements of 9 by 9 meters footprint. Actually only 5 different types because they're repeating. Looks much easier. It isn't because this time the girders are not nicely passing each other. They're intersecting, which means you have 5 layers of beams with lap joints in between, 15,000 of them on the whole roof. This is what you know already. You have glue laminated blanks that you put into a machine like that. Looks a bit newer this time, different fabricator. And then you cut all those lap joints and details and stuff directly on the machine. Planing. And out comes a beam like that. 3,500 of them. You box them into containers and then you send them off to South Korea. While they're on the way, you do a bit of other things and then you ship 30 timber guys from Switzerland right behind them on next plane to pre-assemble those crown elements. They have the footprint of 9 by 9 meters, so 81 square meters. This is basically the size of a nice single family house dangling on the crane here. They're pretty proud. This was the first thing you can see here. On the second one, they had the South Korean flag. And then dangling on the crane, you put one next to the other to build this roof on 21 columns. And the interesting thing here is, oops, this is the connection point between 2 of those elements. And you have a 2 millimeter gap between those elements. So you have a single family house on the crane and you put it down with a 2 millimeter gap on either side. And it works. I was amazed. I wasn't there. I just saw the pictures. Oops. This is what the end result looks like. But on the other hand, it means you're actually moving the whole work forward. You have to really detail the things down to the very last millimeter, to every single connection detail. Digital fabrication always means prefabrication. The machines usually don't stand on the construction site. They're not even close to the construction site. In this case, they were 10,000 kilometers away. So you build all those components nicely and intricately detailed. You put them in a container, you ship them somewhere, you erect it, and it either fits or it doesn't. And if it doesn't, you don't have any chance to change anything anymore, other than flying back 10,000 kilometers, switching on the machine again, and then probably checking into the first-class flight from Zurich to Seoul with the timber piece. And that means you're not spending any money on the construction site anymore. You spend the money way beforehand in the planning process, which means you have to think about your usual budgets that you have in the building industry. 30% of the budget is spent on site. Planning budget or architect's budget. It is not happening anymore. Prefabrication works completely different. And this is the last project I'm going to show you. The Performing Arts Center in Kristiansand. Kilden is the Norwegian word for source. Designed by ALA together with timber contractor Trebuggerit from Norway. Actually a boat builder's workshop again in Norway, Riise Trebåtbyggeri, Bluma Lehmann and SJB. This is again the rendering from the architects from the competition phase. Actually it is a concrete box on the back side with a rather dramatic front towards the harbor of Kristiansand. It's a waved wall with a straight upper edge and a curvy lower edge, cantilevering 35 meters, divided into two parts with this glass wall. The foyer of the opera and theater is on the inside, and the rest is basically a very high dangling wall. The idea was originally to build this as a steel structure. So you have a straight steel beam that is suspended from the concrete box. Then you have curved steel tubes that define the shapes, and then a few layers of plywood, and on the outside oak boards running down the facade. This is one of, I think, 2 mock-ups they built in Norway to find out it doesn't work like this. The problem actually is that there is CNC bending of steel tubes, but from a certain dimension on, you can only bend arc segments, which means if you need to have a continuously curved beam, you have to cut it into short segments and then weld it back together, which means in the end you would end with about 3,000 segments that have to be welded together. And if you know about welding, you know what that means for precision and tolerances. It doesn't work. It doesn't really work, because the idea of the architects was, it's hard to see here, that you have a nice pinstripe outfit actually on the outside with 10 millimeter gaps running up the whole facade in straight lines. And then one day I got a call from the timber guys in Norway that we worked on this camera obscura project 3 years ago, or 3 years before that. I'm saying, I've seen 2 of those mock-ups that don't work. We have to do something. Would you help me to convince them to build the whole thing out of timber? Because, as you've seen already, you can put a timber beam into a CNC machine and basically cut every shape you like out of the timber, which means continuously curved beams are not a problem at all. This is what it looks like. And then you only have to convince the guys that you're not building the whole 3,500 square meter facade on site with a large scaffolding underneath, but you do a prefabrication concept like this with 126 facade elements that are all built after this principle, with 2 straight beams and a series of curved beams and up to 180 oak boards that actually are the visible skin of the whole thing on the outside. Every element is hanging on the steel structure that is still there, so those are the timber beams, and it's completely prefabricated on digital machines and pre-assembled and shipped to site. Again, we had to reconstruct the geometry to fit this construction principle. It was pretty close, but not in every point. So here is the reference surface of the facade. As I said, it's about 100 meters wide, 22 meters high, and 35 meters cantilevering to the outside. And this upper edge is really completely straight, which is leads to some interesting problems, because as soon as you start working with material thicknesses, it's very hard to define where a straight roof edge actually is. But we managed to do that in the end also. There was a parametric model of the full thing in Switzerland at our office in Zurich. So the red part was basic, the concrete was basically almost on site when we entered the project. So the box was there. The steel structure was more or less lying on the ground, completely planned, but not yet erected. And the white part here is the timber part that we still had to design at this point, which was sort of a challenge, because you had to tell the steel guys where to drill the holes to connect the whole thing before you even had the structure designed. But anyway, we had a structural engineer close by Zurich in Eschenbach in Switzerland who did the complete modeling of the thing, which was also a challenge. And we had again this 5-axis machine in Switzerland in Gosau, that did all the curved pieces, which looked like this, 1700 something. We had the boat builders up in Norway with a machine like that, who cut 12,500 oak boards to measure, because of course they also were all different, always 4 at a time. Looks like that. Already with the holes to screw them to the main structure, nicely numbered. This time again the numbers in the material. I'm so glad. Then everything gets shipped to Norway to the boat builders, including the straight beams. They were cut at Tribyggerit in Norway. So we had 3 different fabricators basically in the project, 2 in Norway, 1 in Switzerland. They put together those frames with little laser reflectors here to measure that they were precise. You can see they're standing on jigs here that were also planned in the whole thing. And every connection here is basically self-positioning. So there's always a little slot where things just snap together, which is really important, because if you want to build those things, you cannot measure. Everything is curved. With your meter, you don't have any chance to actually measure exactly on this structure. That means to put on those 180 oak boards, up to 180 oak boards onto the structure, had to be done without measuring. Which means for every oak board there's a little seat cut or notch in every of the curved beams, summing up to 55,000 something. The timber fabricator in Switzerland almost fell from his chair when we proposed this. Said 55,000 notch it takes about 5 seconds each. The rest is pure math. You can do it at your own. I said, that'll cost us a few extra weeks of work on the machine at 150 Swiss francs per hour. Fortunately, we had a timber contractor that knew the whole process and said, yeah, but those guys here would add a few man-months of work when they had to measure all the boards in there. Easy calculation. We mill all the seat cuts, so that every single board just snaps into place without thinking. If you take the right board with the right number and you put it in the right place, the thing comes together like an IKEA shelf. A big IKEA shelf. Those elements are up to 50 square meters each, which means it's only possible to transport this in Norway because the building site is right next to the harbor, and the assembly takes place in the boat builder's workshop, right next to the water, of course. So we actually ship those things on big barges. No way that you can land transport that in Norway. Again, assembly plans, and then you hoist up those finished elements into the steel structure. You see here the red things here. There are, I think, it's hard to see, about 8 holes in every element, 4 on either side, to connect the straight beam to the timber to the steel beam. In the end, it took about 1 element. 4 people on site managed to erect 1 up to 2 elements a day in the end. So they were quicker and quicker by the time. And you can imagine what it means if you have the steel structure. The steel guys tell you, yeah, we have tolerances are about 30 millimeters, plus minus 15, that we can manage to handle. Here you have those 10 millimeter pinstripes going down the whole facade, which means they should be continuous from element to element, which means you need to have a precision on the outside of plus minus 1 millimeter, basically. That means you're measuring every single bolt hole in the beginning to ensure that they're at least within 15 millimeters plus minus, or otherwise the steel contractor would have to rebuild the whole thing, because that was in his contract, fortunately. The same thing happening with the glass facade, of course. Basically, the timber wall is interrupted at the glass facade. The glass facade goes through the timber wall with a 5 centimeter gap, like that. And this is what it looks from the inside. So in this case, it was really important to actually have teamwork running in the whole thing. We had, this is what it looks like finished. And this is what the team looked like. So you have a client up there, you have a general contractor, an architect, and a project engineer in Norway. Then you have a timber contractor in Norway and a timber fabricator in Switzerland, an engineer in Switzerland, us in Switzerland, and the boat builder guys in Norway. And somebody has to figure out all the interfaces and the communication so that everything fits together on site in the end. Which means the old model of having design, engineering, detailing, fabrication, logistics, assembly, only talking to each other via this interface is not working anymore. You have to come together. Half of the time we were working on this project, basically we spent in meetings either online or actually sitting around the table to find out how we do things, to find out how we can fabricate things, to find out if we do those 55,000 seat cuts, to find out how things are assembled, how things are brought to site, what the maximum size for transportation is, and. And that means you have to talk to the people. If you really want to reconnect design and production, you have to talk to those guys a lot to find out what they know, because they will tell you. Unfortunately, most of them will only tell you if they have a contract, of course. But in the end, they're telling you their best tricks, and this is what we actually want to do. We want to get the best tricks out of those guys and get them forward in the design process to talk to you and to find good designs, good detailing, good fabrication methods. Thank you. I hope there's some brains left for questions.
You have shown us a lot of curved beams, double curved beams, CNC CAD milled, but you also showed bended wood and laminated wood beams.
Yeah.
How this works, CNC bending and laminating, that you come on to a tolerance, what fits to the project?
Yeah. That's the main difference between timber and steel. You can bend steel tubes, steel profiles, and you can bend timber lamellas to laminate curved beams, and you have the same problems on both sides. Namely, the tolerances are within probably plus or minus 5 or 10 millimeters. Because also with the lamination of the curved beams, you have to imagine you have straight timber lamellas. You put them into a pressing form with glue in between, and then you close the press and leave them in there for a couple of hours until you put them out. And as soon as you open the press, the whole thing springs back a little bit, which means it's mainly a matter of experience to get the shape that you actually want, both in timber and in steel. The good thing with timber is you can take the timber beam, which is within probably plus minus 5 or 10 millimeters, and put it into a CNC machine that mills it down to probably 5/10 of a millimeter precision, which is what you can't do with an I-beam that is curved. Which means you reach completely different tolerances or precisions on the timber side compared to the steel side, especially when you take into account that you can also fabricate all the detailing directly on the same machine on the timber side. So all the slots and notches and drilling holes and lap joints and whatever is directly fabricated on the machine, which gives you a completely different approach to connection details in this field. This is basically the main difference, and this is why we have so many timber projects at the moment, because it's a great material to build around curves with high precision.
Amazing work. I'm really impressed. I have a question about one assumption you make is, if I remember well, it was digital fabrication is prefabrication. Do you think it's possible to come one day on site with digital fabrication?
Depends on what you mean. I mean, there is attempts to put KUKA robots and stuff on site. On the other hand, the machines we have seen here, they're standing in their own fabrication hall. I mean, you have a machine that's worth probably €500,000 and needs a full-grown fabrication hall of about 50 meters length and 20 meters width to work in a rather controlled environment, because the machine is rather allergic to moisture and dust and whatever. Dust not so much, but moisture, temperature. When working with timber, you have to have a rather controlled environment as far as moisture is concerned. If you're working with steel, you have to have a rather controlled environment as far as temperature is concerned. From my point of view, it makes complete sense to do this high precision work in a really controlled environment where you know where your machine is and then ship things to site. But there's other things. I know of a fabricator that does standing seam panels for roofs and has his fabrication equipment basically built into 2 big Euro containers that he can ship on site, which makes sense from this point of view because the raw material they're using comes in big coils of sheet metal, basically. And if you want to have a standing seam panel on a large roof, it makes complete sense to have large or long panels without any seams that only make problems in water coming in and stuff like that. So what they do is actually they ship the fabrication equipment in a container to the site, and then they roll form their standing seam panels off the coil up to 150 meters length. The company is called BEMO, B-E-M-O, in Germany. And they're actually doing CNC manufactured doubly curved standing seam panels on site, which works in this case. It's a highly specialized machine that they ship to site, and it makes sense because the result are components that you cannot transport anymore. They're up to 150 meters long and they're curved, so there's no way of actually getting them from A to B on a truck. As soon as you have components that you can put on a truck, it makes more sense to fabricate them in a nice little controlled factory hall. And since architecture is mostly made out of components, you can also chop the components a little smaller usually and put them into a truck instead of making them so big that you cannot transport them anymore. So, and even if you transport the factory to the construction site, you have to do the planning beforehand. I mean, also this machine is controlled by digital data that has to be defined beforehand somewhere because things have to fit together. So this actually doesn't really matter. You're moving the effort forward in the process. You're moving it from the site to the planning of things.
Sorry, another question. Do you think that using sensors or I don't know, some adaptive way of having the digital fabrication can adapt to the non-precision of the building site? Like you experienced it with the metal structures. Do you think it would be possible to have a digital fabrication that could adapt? Like today we have people when they're on site, they have to adapt all the time to what is on the plan to the actual site.
It would be nice. It would be possible now also. I mean, you could theoretically wait until the steel structure is there, then you make a survey with a laser tachymeter or whatever take this data as the basis for your parametric model for planning all the rest. Would actually be no problem in terms of technology, but is a big problem in terms of scheduling. Because usually you don't have the time to do that. You can just take into account that laminating the 1,700 beams that are needed for fabricating this facade alone takes about 8 to 10 weeks. So if you wait with ordering the beams until you know the precise measurement of the basic structure, you have a 10-week waiting period. And then you have a 10-week fabrication period where those 1,700 beams run through the machine until you can start doing something on site again, which doesn't fit the usual scheduling in those projects. No way. Those roof guys I was telling you, they actually do laser measuring of the structures they clad. But since they're actually fabricating on site, the cycle is much smaller. They just deliver the coil and the machine, and then they start rolling. So I guess it's all this theory, a practice gap, basically. In theory, it's perfectly possible to measure the things first and then start fabricating. In practice, it's not possible, at least not on this type of structures. That means somehow you have to close the cycle. Sorry, long answer. I have to get shorter.
Yeah, thanks for the amazing lecture. I think like any question will sound naive with the massive work.
There's no stupid questions. Go forward. There's only stupid answers.
I was wondering, this is more like maybe kind of theoretical question. It's related with the fact that the name of digital fabrication is talking about some process that is not digitized yet. We are having digital information using computer control machines, but then at the end we have analog materials. We have like very stupid materials that we are cutting with very expensive tools that needs to be controlled in a very specific environment, as you said now. How do you see evolving it to really come in digitized? How we can, I don't know if in your research is somehow envisioning how that you can put code into materials and how you can program the materials itself in order to build self-assembly structures and things like that, and more like the nature kind of thing.
Yeah. There's a lot of research going on in this field. We're more concerned with the practice of building, which looks completely different at this stage, at least. It's a matter of budgets, it's a matter of time, it's a matter of skilled labor or unskilled labor. Most of these rocket science ideas and materials simply don't fit to the budgets in all the building projects you know out there. That's one of the main things. So all the ideas of shape memory alloys, carbon fiber, whatever things and so on are fine within Formula One racing, but probably not within building large-scale structures, simply because of the budget. Also because it doesn't fit the process around it. I couldn't imagine building a facade like this out of carbon fiber or whatever, because in the end, the whole construction site around it is still based on steel, concrete, and tolerances of plus minus 15 millimeters. And it's not going to change, I'm afraid, quickly. You'd rather have to, what we're trying to do is we try to smoothen the process as it is on exactly those places where time or money are lost in the things that we're doing right now. That's the strategy for us for the moment. And I can tell you there's lots of places for enhancement in building processes out there.
Okay. So, what is your insight about digital construction? Let's say in the on-site digital, like a vision.
A vision, depends a bit on what you mean by that. I mean, we are mostly concerned with doing the planning work in those projects, which actually I don't really care if the digital part where the materialization happens is happening on-site or off-site. The only thing that really matters is if something is wherever fabricated on a digitally controlled machine, someone has to think about it first, because someone has to come up with the digital information that drives the machine. The machines don't do that themselves. And that means the approach of, okay, we have a heap of material like bricks, and we have we just put them together on site one by one is not working anymore in this project. Either you have a robot putting bricks together, which happens, but someone has to program the robot beforehand and test those programs and all those methods beforehand, so that he can be more or less sure, or she can be more or less sure that things are put together on site in the correct order and way. Or you fabricate them off site and assemble them on site, and also have to plan ahead every single piece, more or less. But it doesn't really matter. Digital fabrication means you have to have the digital information first before you can do something with the material. And that means moving forward the effort in the building process, from moving material to moving information.
So, one more question.
Yeah.
I need a drink.
The question is, after all this work that we've seen, that you have worked with one of the most important architects nowadays, and we hear you criticize in some way the huge distance between concept and fabrication process. So the question is, what's next in design to production? So if you are
the next step actually would be nice to talk to the architects in the first place, because I rarely ever meet them. We're doing a lot of work in those projects after tender, only working for the fabricators. The first time I met Shigeru Ban was about 2 months ago at a speech he gave in Zurich. And he probably doesn't remember me. Which is okay for me. I understand myself as a service provider to architects, engineers, and fabricators. At the time being, I'm being approached mostly by fabricators who have to sort out things that land on their desks. I would like to work more for architects, but there is sort of a collision with the process of architecture, which means, or not with the process of architecture, but with the process of building, which means we're spending all the money at the end of the process, not at the beginning of the process. And that's basically the next thing that has to happen. Is when we're talking about digital fabrication and about moving the effort forward in the process, because planning has to be at a certain stage before fabrication actually can start. That means you have to move forward the information in the process and think earlier in more depth about fabrication, assembly, and all things happening on site. And that means if you shift the effort forward, you have to shift the budgets forward. And that means as long as the architects don't have a budget for actually asking specialists like fabricators, engineers, or ourselves early on in the process how things are being built in the end, of course they don't do it. You have to make a living. I have to make a living too, which is I won't tell you all my secrets before I have a contract and get money for that. And there we have a problem. This usual design, tender, build process is not working on those special projects. It's perfectly working on standard projects. It's easy to tender for 300 running meters of straight brick wall. It's rather difficult to tender for 3,500 square meters of curved timber wall, because you cannot even describe what you want a fabricator to do in the first place. Neither can you describe how the solution actually should look like. before you have talked to a number of fabricators, which is a problem because they won't tell you the best tricks before they got the contract. And this is something where we really have a clash in the process right now that has to be resolved one way or the other.
So Ali, last question and we stop, okay?
I want to ask you a question about the Sana project. Like, you showed us the big timber structure, and in a way, like, how you managed to, like, after constructing the whole thing, what happened to those timber boxes? And what was the expense according to the whole project?
I don't actually know what the expense was because no one's telling us the real figures. I only know my budget. The timber boxes were shredded and, as they call it, thermally recycled, which is a pretty neat idea to do with timber because they press them into pellets and they put it into standard heating systems, which is pretty fine with me. After all, it was about 20,000 square meters of plywood, which is an amount of timber that basically grows in Switzerland within 10 minutes. And the rest is a bit effort for fabrication and stuff like that. Another good argument for timber structures, I'd say, even if you take them away and just leave the concrete there, as opposed to probably milling concrete formwork out of extruded polystyrene or stuff like that, which is another option that was discussed, but was impossible due to the scaling problems that I tried to explain in the first or second project. Yeah.
Thank you.